So these notes are on thermodynamics. It is one of our last topics until we're ready for a test. So we've been talking about how heat is exchanged or energy is exchanged when our solids, liquids, and gases heat up or cool down. We've been talking about the heat needed to cause an object to melt or vaporize, and the energy that's released when it freezes or condenses. Thermodynamics, now we're talking about the study of the changes of heat in chemical reactions. So remember in our bar graphs we had ETH, right, our thermal energy, which was really just kind of the kinetic energy of our molecules. And then we had the interaction energy, which was um, changed when we went from solids to liquid to gases. And now there was that other one, that other bar graph that we didn't use, and this is it. Now, we're not going to go and make new bar graphs or anything like that, but we are going to talk about how energy is absorbed or needed to make a reaction take place and how it can be released in certain chemical reactions. Now, if we move on the next slides and it goes too fast, remember it's a video. Just pause it, write down what you need to write down, and then move on. Now, we already talked about these terms, endothermic and exothermic, right? Exothermic energy is exiting. So it can be exothermic if a liquid is cooling, or if a liquid is freezing, or a gas is condensing, or a gas is cooling. Well, it can also be exothermic if a reaction releases heat when that reaction takes place. And endothermic is saying that it absorbs heat or that it needs heat for the reaction to take place. It needs energy to make that reaction happen. So enthalpy is what we're talking about, right? We talked about thermal energy, interaction energy, now we're talking about enthalpy. And really enthalpy, when you see this delta H here, all that really is it's kind of a third way of looking at an exchange of heat, right? We talked about a lowercase q being used when the temperature changed of our solid, liquid, or gas, and a capital Q was the energy that was needed or was released when we went through a phase change. Now we have delta H, and really they're just all ways of saying the same thing. How much energy is exchanged during this process? And in this case, we're talking about a chemical reaction. So the heat absorbed or lost during a chemical reaction, right? We know that exothermic, right, it exits, and we said that exothermic, if it was exothermic or it was releasing, it was decreasing in temperature, our Q would be negative. And if it was phase changing and it was condensing or freezing, it would be exothermic, and so we'd have a negative Q. Well, if it's a reaction and it's exothermic, well, it's still negative. And of course, that means endothermic is positive. So if our temperature was increasing, if our solid was melting or our liquid was evaporating, and now if our chemical reaction is absorbing heat or it needs heat to take place, right, it's endothermic or a positive delta H. Pretty easy though, these steps. It kind of looks like stoichiometry, except for our stoichiometry problems were always 3 steps long. These are only going to be 2 steps long, but we're still going to need to do some conversions in there with moles, and we're going to need to use a balanced equation. So always make sure that your equation is balanced. So it says here, right, given an equation, you can use the delta H of the reaction to find the delta H of a specific amount. So really what happens is you're going to be given this delta H value, and it's going to tell you how much energy was released basically per however many moles are in the reaction. So I'll wait till we get to an actual reaction to try to explain what that means a little bit further. So We're going to convert grams to moles, right? If we were given something else, we would convert it to moles. If we were given a volume or if you were given a number of particles, we always want to convert it to moles. But really, all your problems are going to start with your substance almost always in grams. It could be in liters, but it's always going to be pretty much in grams. And we know that we can convert grams to molar mass, and remember that molar mass needs to be rounded to 1 decimal place, and you get all those masses from the periodic table. Our second step, right, convert moles to kilojoules using the delta H relationship established in the equation. So you're going to see in a second that it's going to list how much energy is absorbed or released during the chemical reaction, but it's going to be in the unit of kilojoules this time instead of joules. So here's our example, right? 2 moles, right? 2 moles of our hydrogen peroxide decomposes, right? It decomposes into 2 moles of water, and it's understood that it is 1 mole of oxygen. So our delta H over here, what that tells us is that tells us that 190 kilojoules of energy is going to be released when 2 moles decompose into 2 moles of water and 1 mole of oxygen. So when we get to that equation and we use this in a fraction, whatever substance we're dealing with, and we're talking about the number of moles, you have to use the coefficient from the balanced equation to go with that number, right? It's 2 moles decomposes and releases this much energy. Or if 2 moles of water is formed, you need this much energy to be released, or 1 mole of oxygen. Okay, so here we go, right? What is the delta H for 1 gram of H2O2 if it decomposes, right? It's going to decompose. It's a negative value here, which means it is exothermic. Energy is exiting the system. We're going to take that 1 gram. We are going to make sure that we get rid of the grams of H2O, so our molar mass needs to be on the bottom of the fraction, right? And we convert it into moles. So 1 mole of that substance has this mass, right? I'm not using my coefficients from the balanced equation because 2 moles doesn't equal 34.08 grams. Just 1 mole weighs 34.08 grams. So now we're in moles of our hydrogen peroxide. And then, as I said, 190 kilojoules is released when 2 moles decomposes. So our bottom is 2 from our balanced equation, and now the moles of hydrogen peroxide cancel out, and we are left in the units of kilojoules. Our initial value, right, has 1 sig fig here, or sorry, 2 sig figs here, and so our answer goes to 2 sig figs, right? Negative, so 2.8 kilojoules of energy is released when hydrogen peroxide decomposes. When 1 gram of hydrogen peroxide decomposes into water and oxygen. Okay, here we go, another one. What is the change in enthalpy when 9.22 grams of C6H12O6 reacts? Right, well, that is a hydrocarbon compound. So our hydrocarbon compound is burning in oxygen, right? It's a combustion reaction. It always produces carbon dioxide and water. When that equation is balanced, we can see that 1 mole, right, of our C6H12O6 is going to release negative 2,803 kilojoules of energy. Right? If it told us how many grams we had of oxygen reacting, then we would say 6 moles is going to release 2,803 kilojoules. But in this case, it's our C6H12O6, so it's only going to be 1 mole. So we're going to change that turn that 9.22 grams into moles, right? So how much does 1 mole weigh? We've got to add up 6 carbons, 12 hydrogens, and 6 oxygens, which is 180.0, right? Go to 1 decimal. And then our reaction here, right, is, like I said, 1 mole of our hydrocarbon compound releases 2,803 kilojoules of energy. Our units of grams cancels out, right? Our units of moles cancel out. We're left in the unit of kilojoules, and so negative 144 kilojoules. So 144 kilojoules is released when that reaction takes place. And that is it. There's your notes.